section 3.2 is about mathematical induction. This is a great way for us to prove numerical statements and theorems. So the first thing we need to know in order to use induction is that the well-ordering principle exists. And what the well-ordering principle is this, is that if I have a non-empty set of numbers S, it's said to be well-ordered if every non-empty subset of S has a least element, so a smallest element. So let's take a look at S equals -7, -1, and 2. That's my set. Its non-empty subsets are everything I would have found, for its power set except the empty set, right? So I have the whole set itself, I have all of its size 2 subgroups, and I have all of its size 1 subgroups. Each of these subsets has a least element. The least element of our first subset's -7. The least element of our second and third subsets are also -7. The least element of our fourth subset's -7, and then all these sets of size 1, the least element is just itself. So because of that, it's well ordered. And we can we're going to take this as an assumption that every non-empty finite set, so finite being countable, of real numbers is well ordered. Okay, so every finite set of real numbers is well ordered. So let's take a look at some places where things wouldn't be well ordered. So if I have an open interval, right, an open interval on the real number line from 1 to 2, it's not well ordered because it has no least element, right? I can get really, really close to 1, but 1's not included. So is it 1.01? Would it be like 1.0000001? It goes on forever, so it has no least element. The closed interval, okay, the closed interval 1 to 2 does have a least element, but remember that it's not just the set itself that needs a least element, it's every subset. So because 1, 2 is a subset of our closed interval, this doesn't have a least element and every subset does. Okay, so let's think about our number families. We'll think about the integers, right? And we'll think about the real numbers. These are not well ordered because neither of them have a least element. However, when we think about the set of natural numbers, n, right, that's well ordered. The smallest natural number is 1, right? It has the smallest element of 1. So let's start to talk about induction. I'm going to go through some proofs. I've included an extra worksheet in this module of some worked out induction proofs. It really just takes some practice and just some number manipulation. So let's go ahead and introduce what mathematical induction is. Mathematical induction is a proof technique that's used to prove a propositional function is true for all natural numbers larger than a given value. So there's two parts. The first is our basis step, right? This step involves proving that our propositional function is true for our first natural number, which is 1, right? The second part is our induction step, where we prove that if our propositional function works for n, right, then it's also true for n plus 1. It's going to be true for every natural number. So the principle of mathematical induction, that's theorem 3.2.1 in your text, says this. Suppose we have a propositional function s of n, so it's a function, right, with domain equal to the natural numbers, because that's a well-ordered set. If we establish the following two steps, then s of n is true for every n in the natural numbers. So the first thing I need to do, s of 1, our first element of the natural numbers, is true. Then we use our induction step where I say if s of k is true, then it must be true that s of k plus 1 is true, where k is any natural number and k is greater than or equal to 1. Okay? So some people write these proofs more formally. Others don't. We know I'm not the most formal proofwriter, but let's go ahead and practice. I'm going to go through 2 proofs in detail. I have also included all of the solutions in this PowerPoint so you can see your work without watching the video. So let's go through our first example. I want to prove that 1 plus 2 plus 3 plus ... right, all the way on to n equals n over n plus 1. So let's go ahead and check our S of 1 case. So let us see S of 1. So that means that 1 equals, I'm plugging in 1 for n, 1 times 1 plus 1 divided by 2. Well, 1 times 2 is 2 over 2 is 1, right? So, okay. So we have S of 1 is true. Let us assume S of k is true for some positive integer k, or k greater than or equal to 1. We then have, let's plug in k. We then have 1 plus 2 plus 3 plus ... k equals k times k plus 1 over 2. We must show S of k plus 1 is true. So what is true? And we find, now what you're going to want to do is substitute in k plus 1 into this. So you're going to find 1 plus 2 plus 3 plus ... k plus 1 equals k plus 1 times k plus 1 plus 1. Well, we want to go ahead and simplify this, right? K plus 1 is k plus 2. So I'm just going to erase that because I know we're never going to have enough room. Okay, so I need to prove that this exists. Okay, this is what I need to find. Okay, so the first thing I know, I have S of k is true for some k. That's the one thing I've said is true. So I've got 1 plus 2 plus 3 plus ... plus k equals k times k plus 1 over 2. Well, I need to get this in blue to look like this in orange. So I have to add k plus 1 to both sides. So I get 1 plus 2 plus 3 plus ... plus k plus 1 equals k over k plus 1 over 2 plus k plus 1. Well, in order to add fractions, they need to have the same denominator. So I want to just focus on simplifying this right-hand side. So I can rewrite k as a fraction by multiplying it by 2 over 2, right? Because my denominator here was 1. So now I have 1 plus, now here's something I want you to know you can totally do. If you don't want to copy all of this, you can use quotation marks. Put quotation marks there, and then if you do that again, I'll know, especially if you're typing it up, you can use the quotation mark shortcut. That's going to equal k times k plus 1 over 2 plus 2k plus 1 over 2. So I can go ahead and add those. There's never enough room. So this equals k squared plus k plus 2k plus 1 plus 2 all over 2. Okay, what did I do here? Well, I FOILed this out and I added them. So I'm going to rewrite this, I guess, over here. Please ignore my little step. Okay, so now I have k squared plus 3k plus 2 over 2 equals our quotation marks, right? All of this hot mess. Well, I need to factor this quadratic. So remember, going back to college algebra, right? If you need me to post stuff on factoring, send me an email. I'm happy to do so. But I find the factors of AC, which is 2, that add up to B, which is 3, and that's going to be 2 and 1. So this equals K plus 1 times K plus 2 over 2. Well, look, we found what we needed to find. We needed to find this. And we did, right? We're manipulating to get to our K plus 1 step. Okay. Here it is typed up more neatly. Step by step. Okay? Say you're going to use induction. Prove that S of 1 is true. Assume S of K is true and use that to show, right, this is S of K. We use that to show that S of K plus 1 is true through manipulating typically just the right-hand side. I did tell you what to do every time. Here you wanted to add. Simplify the right-hand side by adding, right? Okay. So I feel pretty good about that one. Let's do one more before I talk about your homework. Your homework isn't a ton of problems, but it could be long. Again, if you are typing this stuff up, don't feel like you have to retype this. Excuse me. Every time, feel free to use quotation marks, and I'll know what that means. So let's go through another example.